Hello there, Mr. Sutton here, bringing you the Algebra 2 6-7 Part 2 homework solutions on modeling exponential and logarithmic functions. The first couple problems, we're trying to figure out what type of function is represented by the data in the table. So for each of these tables, we're basically going to see if we have any common differences or common ratios and go from there. For this first one, we see that if I do times 4, that gets me from 0.25 to 1. And then 4 times 1 is 4. 4 times 4 is 16. We've got 4 again, and another 4 gets us to 256. So there is a common ratio going on here. That tells us that this first one must be an exponential function. For this table, just looking for common differences and ratios, let me check for a common ratio first. So we have 3/4 for the first one, and then 7/3 for the next one, and very clearly we're not multiplying by the same thing to get each successive y value. So let's take a look at common differences instead. We got 3 minus 4 is -1, 7 minus 3 is 4, and it's not a common difference right away, but we know that if we go down a few levels, we might see a common difference, so we have to kind of stick it out for a while. 16 minus 7 gives us 9. 30 minus 16 is 14. And then 49 minus 30 is a difference of 19. All right, let's go down a few more levels. So 4 minus -1 would be 5. 9 minus 4 is also 5. 14 minus 9 is 5. And 19 minus 14 is 5. Since the second difference is a common difference, common second difference, that means this is a second power polynomial function, also known as a quadratic function. For this problem, they want us to use technology, namely Desmos, to determine if this data fits an exponential model, and if so, write that function. So let's go to Desmos and plug all these in a table. So here I am in Desmos. Let me press this plus here to get my table. So we've got x values of -20, -13, and it looks like it's going to autocomplete to give me these common x value intervals. So we got 1, 8, and 15. There we go. For the y values, we've got 25, 19, 14, 11, 8, and 6. Let me press the little magnifying glass to get zoom fit there. And then let me do my regression. So I'm going to select exponential regression for this. And it looks like 0.9994, that's our r-squared. That's a pretty good correlation there. So here is my graph. Definitely, this is an exponential with that kind of a correlation. And then just taking a look at the equation here, we have about y equals 11.16008 and times 0.960391. All that, we'll just cut and paste that here. On this problem, they want us to use technology to see if this data fits an exponential model, and then if it does, write a function for it. So let's go to Desmos and plug these in a table. Let me press my plus button here to get that table. And now for the x values, we've got -8, -5, and then it autocompletes, giving us intervals of 3, it looks like. For the y values, we've got 1.4, 1.67, 5.32, 6.41, and 7.97. And let me get a zoom fit to get a little closer in there. It doesn't really look all that exponential, but let me try a regression anyway and see what kind of r-squared we get. Exponential regression. And the r-squared on this one is 0.89, which sounds kind of high, but actually is kind of low. That's not a great correlation. We're looking for something at least like 0.9798, if not higher. So based on what we've seen there, an exponential model is probably not the best fit for this one, and we're not going to bother writing a function for this. On this problem, we have a store selling electric scooters. This table shows the number of scooters, which is the y value, sold during the xth year that the store has been open. So that's our x values. So for example, on year 6, we sold 53 scooters. We want to use technology to find an exponential model for this data, and then use that to predict how many scooters we will sell during the 10th year. So to use technology, that means go to Desmos and enter your table in there. So here's Desmos. Let me press the little plus to get a table. So we've got 1, 2, and all the x values are going up by 1, so that's pretty easy to get through. And then for the y values, we've got 9, 14, 19, and let me move this a little bit closer so it's a little more centered. Then we got 25, 37, 53, and 71. All right, let's do a zoom fit. That's this magnifying glass. And that looks fairly exponential. Let's do the regression here. And then we'll click on exponential regression. And we see our r squared is 0.9981, so that's a very high correlation. It's pretty close to 1. So that's pretty cool. They want us to find the model now. So that is this 6.911 times 1.397 business that they have in there. And then we're going to figure out, using this, what the 10th year gave us for scooters sold. So we'll plug 10 into all this. And just to be super accurate, I'm going to use the original, not the rounded off version that I have here. So to do that, let me go to my equation button here. If I press that, that copies it down there. Let me rename this to f of x. That'll allow me to plug things into it. And I want to plug in 10 specifically, so f of 10. And that's about 196 if I round it off to the nearest scooter. On this next one, we have a clay pot with a temperature of 160 degrees Celsius, removed from a kiln and then placed in a room with a temperature of 20 degrees Celsius. And then this sounds like it's going to be like a Newton's cooling law problem, but they just gave us a table with all the temperatures of the clay pot at different times. So that the input is the temperature, and the output apparently is the times, which is kind of interesting. They want us to use technology now to find a logarithmic model in a plus b times ln of d form that represents this data. And then they want to estimate how long it takes the pot to cool to a temperature of 50 degrees Celsius. So let's start by going to Desmos and entering our table data into a Desmos table. So here's Desmos. Let me press my plus to get a table out of this. And we've got 160, 90, and it's going to autocomplete, but we don't want to take the auto-completed values. 56 is not 20, so we're going to actually plug those in manually. And then we have 38. And then what's my next value? Let's see, 29, and then 24. And then going back to get the x values, I think those are just, yeah, those are just 0, 1, 2, 3, 4, 5. So those are pretty easy to put in. Those don't autocomplete, but we know what they are. All right, so to get, first off, let me get my zoom fit just to see what this is looking like. And this does look kind of logarithmic here. Looks like there's some kind of asymptotic action going on there. Let me click on my regression button, and I'm going to choose logarithmic regression right here. And the r squared is not fantastic. I mean, 0.9655. It's not horrible, but I would say this is kind of a mediocre sort of correlation, at least compared to the ones that we've seen. But we'll use it. So here's our graph. Here was the, let's write down the equation, which was 12.593 minus 2.546 ln of x, this thing here. And then to figure out how long it takes the pot to cool to 50 degrees Celsius, we just have to plug in 50 for the t value here, apparently. So let's do that. And then going back to this, if I actually want to use this, I'm going to click on my equation button. That cuts and pastes it here. And I'll just rename my logarithmic function. So f of x is what I'm going to call this. And if I want to figure out 50 degrees, let me just do f of 50. And it looks like that's going to be 2.632. So roughly 2.63 hours is the time it takes this thing to cool to 50 degrees.